it will be 0 degrees. At 0 degree and 1 atmosphere, the volume that any gas occupies is 22.4 liters.
Does the number ever change for the molar volume, or is it always
always the same?
Okay.
All the gases are occupied, but the temperature must be what? 0 degree, and the pressure must be 1 atmosphere.
Okay.
Okay?
Okay.
So you can use that. This is a very important number to consider in calculation.
Okay, perfect. Thank you.
We now have a new unit factor. So we have a new unit factor. All right. One more gas is 6.02 times 10 to the 23rd molecule. Gas, 22.4 liters, that's the volume. So look at that table, 8.1. More relationships for selected gases. H2, okay, they selected hydrogen gas, oxygen gas, carbon dioxide, ammonium, and argon. That's a list of gas in there. Take a look. The number of moles. Hydrogen 1 mole, number of molecules is 6.02 times 10 to the 23rd. What is the molar mass? Well, that is 2.02. What is the volume occupied at STP? 22.4 liters per mole. Don't forget, it has to be 22.4 liters per mole. That's the molar volume at STP, 22.4 liters per mole. So this table very, all gases, you notice that, you see they got different weights, but yet and still, they still all occupy the same volume. But the temperature must be 0 degree and 1 atmosphere. Is that clear so far? So the table is very, very useful. 8.1.
And by.
All right, so we see the box below has a volume of 22.4 liters, which is the volume occupied by 1 mole of a gas at STP. All right, at STP 22.4 liters. Now, let's talk about density. We dealt with density before. The density of a gas is much less than that of liquids. You know, in dealing with the states of matter, we say gas, liquid, right? And what else? So the density of a gases is much less than that of liquids, okay?
So does that mean the gram slash the the liter, right? So it's gram per liter?
Gram per liter. Gases are gram per liter.
Okay.
Or when you're dealing with a liquid, you have what? Gram of a milliliter or gram of cubic centimeter. You know, we talk about the fact that solid is gram per cubic centimeter.
Right.
But that cubic centimeter is also equivalent to one milliliter. So therefore, liquid can be both.
Okay.
For gases, the volume is liter. Keep that in mind. Okay.
Thank you.
The formula for gas density at STP is as follows. So that's what it is. All right. So what is the density of methane gas? Methane is CH4. Now, I want you to take a look at this slide and tell me if you see any mistake that it made. Do you see the mistake made in this slide? Anybody?
Is it the liter per mole?
No. No. No, you don't see anything there? Anybody? Who sees something?
Is it supposed to be 16.04 grams per mole?
Yeah, that's not, we still haven't seen it yet. Nobody see it?
It's not. Oh, never mind. Yeah, isn't it 16.41 grams per mole?
Well, that's not the mistake. What's the mistake they made it?
Do you mean the answer?
Huh?
The answer?
No, just look and see. They tell me, do you see any error? Anybody? You don't see it here? Remember, I told you this slide's got some errors in them. I want you to be able to detect.
Is it supposed to say what is the gas density at ST? Like instead of density, should it say gas density?
Okay, so nobody can see it. Look at his second bullet. Take a look at his second bullet. What do you see in the second bullet?
Gram per mole.
What do you see in the second bullet?
Mhm.
That's right. That's right. You see?
Oh.
You see it now? It's supposed to be what? First we must need a molar mass for what? Methane, right? Instead of methane, they have ammonia. That's what I want you to catch. You got it now?
Yeah.
But the information, huh?
Yeah, because if not, we'd be writing down ammonia.
So now, so we see, but what the calculation below is for methane. See, that one is okay. Methane is CH4.
Oh.
You see it now?
Yeah.
Yeah. So 12.01, that's okay. 4 times 4 hydrogens. So 16.05 is great. It's good. That value is for methane and not, and not ammonia. The molar volume for CH4 at STP is what? 22.4 per mole. That all this part is correct. Density is what? Mass over volume. They have that there. Did everybody see that? So you gotta say 16.05 grams per mole because you see the molar volume has a mole in it, so the mole can drop out, so you can get a density gram per liter. You can't leave out a gram per mole. You're not gonna get the gram per liter there. Everybody see that? So the more cancer, and you have gram per liter for density. All right, so moving right on, we can also use molar volume to calculate the molar mass of an unknown gas. If we're trying to find out what gas we're dealing with that we have collected, but we don't know this gas. So the molar mass can give us information on what type of gas we have. An unknown gas has what? 4.29 grams of and occupies 1.50 liter STP. What is the molar mass for this gas? We want gram per mole. So whenever you hear molar mass, gram per mole should be reflected in your mind. But we have what? Gram per liter, which is the density. See, we have gram per liter, the density. So we're gonna write down we're gonna write down what we have, which is a gram with our density times the molar volume. See, density times the molar volume will give you the molar mass. Okay, density times the molar volume will give you molar mass. Everybody see that? So you gotta be mindful of what's given to you and where you're going. So 22.4 liter over 1 mole. So that gives you 64. And you should also start checking those numbers, making sure that sometimes the numbers are not, but the concept is great. The way to solve the problem is good. All right. So we now have 3 interpretations for mole. All right. Take a look at the 3 interpretations for mole. Make a note of them. The first interpretation is 1 mole is equal to 6.02 times 10 to the 23rd particles. That's one interpretation. You can form a unit factor with that. You can say 1 mole over 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd particles over 1 mole. You generate 2 unit factors. And then, based on what's given to you, you decide which unit factor to use. Okay? So always develop 2 unit factors and either or, and then you look at what we have. The second interpretation is 1 mole is equal to molar mass. Molar mass. So 1 mole to the molar mass, or molar mass to 1 mole. The third one is 1 mole to molar volume, the STP. So this gave us 3 unit factors to use to convert among moles, particles, mass, and volume. I want you to take a note of that. Very important. Okay. Everybody have that in the question? Be able to do the conversion. Now.
Okay, really quick. So 1 mole always is the molar mass, always, right? 1 mole?
Yeah, 1 mole is equal to molar mass.
Okay, perfect.
Okay, you got that now?
Yes, thank you.
Right. Mm-hmm. A sample of methane, okay, CH4, occupies 4.50 liter at STP. So when you STP right away, a bell should ring. The temperature gotta be 0 degrees. The pressure is 1 atmosphere. The volume is 22.4 liters. That 3-year STP, that's your ring bell. So in 1 moles, we have volume. Use molar volume of a gas. What's the molar volume? All right. Go back to number 3. 1 mole is equal to 22.4 liter. That's the molar volume. All right. So use molar volume of a gas, which is 1 mole equal to that. So you're giving 4.50 liter of CH4. Proper setup. So the molar volume is what? 1 mole over liter. So you want to get rid of the things from the starting point. You're getting rid of those things as you move toward the right. Start getting rid of things from left to right. So now, when you set a problem up well, your homework should be set up this way, make it easier. I'll be looking for all that in the homework. So the volume CH4 cancels with volume CH4. Simple. What do we want? What we need is always in the numerator. So we need more of CH4. Then you can multiply. If you were in a regular setting, your exams that you take, you have to show your work. I'm that person who like for students to show their work. It tells me you understand something. So showing your work is an indication of you understand the thing. 10 years from now, maybe your granddaughter, your grandson will come to you and say, "Grandma, Grandpa, how do you find what do you do when you have a sample of methane, CH4 occupied 4. How do you solve that problem? Right away. You go right back. Yeah, I got it. We did it years ago at Harvard College. All right. So what is the mass of 3.36 liter? That's something that's given to you of ozone gas, which is O3, STP. They're asking for the mass at STP. The mass when the temperature is 0 degrees Celsius, when the atmosphere is 1. When that question is raised in your mind, okay, they want to know what is the mass when the temperature is 0 degree and the atmosphere is one atmosphere. That is STP. And the molar volume is 22.4. So every time they ask this question, what is this at STP? You say to yourself, okay, I know what they're asking. They're asking me to find such and such when the temperature is 0 degrees Celsius, when the atmosphere is 1, when the volume is 22.4 liters. Keep that in your mind all the time. The question says, what is the mass of 3.36 liter of ozone gas at STP? By the way. So we want the mass of O3 at STP when the temperature is 0 and the atmosphere is 1. So what do we have? We have a volume that reads 3.36 liter of the ozone. So now we start with that. That's what we have. Start with what you have. 3.36 liter ozone. All right. The molar volume, 1 mole of ozone with 22.4 liter. That takes care of the starting point in terms of the volume. They want mass. So what is the molar mass for ozone? Each oxygen is 16, got 3 of them, so that's 48.00 gram of ozone for 1 mole. So you see, you're going back, we go back to these three areas, the 3 interpretation for mole. How important that is, you're going to be using this here. These are the 3 interpretations going on there, okay? So now we got 7.20 gram of ozone when the temperature is 0 degrees Celsius, 1 atmosphere. You got that now? So that STP should ring a bell in your mind. Now, here's another question. How many molecules of argon gas? The symbol is AR. That occupy 0.430 liter at STP. So at STP, what they're saying to you, that argon gas occupies it's a how many molecules will occupy this volume here at STP when the temperature is 0 degrees Celsius, when the pressure is 1 atmosphere, and the volume is 22.4 liters. All right. So we want what? Molecules. What do we have? We have liter. Okay. So we convert the volume to moles, and then moles to molecules. So you start with what you have. You start with the 0.430 liters of argon. 1 mole of argon is 22.4 liters of argon. That is your what? Molar volume. All right? So the three interpretation they give that we just passed by, that's what we're using throughout now. 1 mole of argon is 6.02 times 10 to the 23rd molecules. So the 1 mole of argon, drop out 1 more argon because we're looking for molecules. So when the problem is set up like this, it's clean, it's very clean, easy to deal with. Put all the units in. Do not leave the units out in your homework. Make sure all the units, one more argon. Say it like that. Lit up, set those things out like that. Make it easy. All right. So therefore, now you have this. Then you go after the significant digits. We got 3 significant digits here. We got 3 there. We got 3 there. So we must have 3 here. All those things, as long as you're taking this class, remember them until August 16th. After that, you can write anything, you can do anything. You're on your own. But as long as you're with me, you're ready to do it. That's what you're supposed to be doing. All right. Now, so let's count the percent. Percent means whenever every time you hear percent, you start thinking 100. Just like when you hear molar volume, you start thinking 22.4 liters. You know, when you hear Avogadro, you start thinking 6.02 10 to 23. See, certain thing when you hear something, a bell goes off in your mind. So when we say percent, we mean we're talking about 100. Percent composition. Something that's made out of something. What contribution each one is playing in that makeup. That's what we mean by percent composition. You find something, it composed of this, composed of A, B, C, and D. But what is the percent of A there? What is the percent of B there? What is the percent of C? What row? How much did you have to put together to make what you have in your hand? In order for you to successfully have what you have in your hand, to be what it's supposed to be. That's how we make things. All right. Now, I just made a mouthwash out of I extracted. I think I told you guys before. I don't know, but I extracted from cinema. Made mouthwash. Maybe one of these days I can catch up with you and let you try. So you gotta make sure that you have it in percentages right. So for example, we gotta have water. To have water, it has to be H2O. It has to be H2O. Okay. So if it's H2O, well, how much is hydrogen in this thing? So the H2O is 100%. Well, how much is oxygen in this H2O? See? Because it cannot be H2O when those percentages are not right. Gotta be right. So for example, the percent composition of water, 11% hydrogen, 89% oxygen. All right? All water contains 11%. Hear that? All water contains 11% hydrogen, 89% oxygen. Nothing else. All the time, it has to be that. All water. Water molecule. Now, water itself is a network. Water hook up to each other. Water molecule is a huge concern. All right, we'll talk more about that when you get to 66. Those of you that are coming to 66 in spring. All right. There are a few steps to calculating the percent composition of a compound. Let's take a look at the few steps. All right, so let's practice using the H2O. Let's assume that you have 1 mole of the compound because water is a network. So now we just assuming that it's just H2O, but it's not just H2O by itself. It's, you have one H2O hook up to the next H2O, hook up to the next through hydrogen bonding. One H2O hook up to the next H2O, and then I want to the H2O. It's a huge, because it's a network. But let's just assume that we look at what I H2O. Number 2, 1 mole of water contains 2 moles of hydrogen. That substrate you see there can be looked at as mole, can be looked at, as molecule, all kinds of stuff. All right. So you have 2 moles, that subscript also designate 2 moles of hydrogen and 1 mole of oxygen. Mole is very, very important. So now we have, since we got 2 of them, each one weighs what? 1.01. So multiply that by 2. The oxygen just got 1 there. Each atom, this is atom now, 16.02. So therefore the molar mass for water is 18.02 grams per mole. That's the molar mass for water. Every compound has its own molar mass. So for water, the more you use it, you will remember it's 18.02. And I'm sure you guys probably got it locked up now. 18.02 is the molar mass for water. Okay. All right. So next, we're going to find the percent composition of water by comparing the masses of hydrogen, oxygen in the water to the molar mass of water. That's what percent means. Okay. A part of a whole. Percent means part of a whole. What is the whole? The whole is the molar mass, 18.02 grams. That's the whole. So we want to know hydrogen, each hydrogen atom. We're going to express that over 18.02 grams of the whole, which is water. And multiply that by 100, that'll give us 11.2. So we come to that. Now, we can do oxygen if we want to, but we don't have to. But if we do oxygen, we have 16.2 over that, than that. But if we did hydrogen, say, okay, I don't want to do oxygen this way. Or what do I do? Can somebody tell me?
Just
What we-
subtract from 100.
Very good. Celebrate that. Yeah, let's celebrate that. All right, subtract the 11.2 from 100. Yeah. Okay, unless I want you to show every one of them. Right. So here's something here, TNT, used during a war, is an explosive called trinitrotoluene. When you get a 66, we'll talk more about that. We'll even show you the structure for that, but it's written in a molecular form. It is a white crystalline substance that explodes at 240 degrees C. This material will explode at 240 degrees Celsius. The way to calculate the percent composition of TNT. What is TNT made out of? It got carbon there, it has hydrogen there, you got nitrogen there, you got oxygen there. We can account for each of those elements. So we're going to know how many of each of those elements in that TNT. Well, we see seven carbon there, we see 5 hydrogen there, we see 3 nitrogen there, we see 6 oxygen. The quantity NO2 taken 3 times, so that 3 will be multiplied by everything in that parenthesis. Okay. So now you're going to add all of that up. When you multiply each one, you add it up, you have a molar mass for TNT. So this is a practice for molar mass. Now, if you want to know the percent hydrogen, percent carbon, percent nitrogen, so the whole is what? 227.15 grams. So we express the amount of carbon, the amount of hydrogen, the amount of nitrogen, the amount of oxygen over that number to find each of them. You see? So, very, very important. Now, this is what they're doing right here. So they're doing that. Here you have, for each of them, carbon, hydrogen, nitrogen, oxygen. All right, just one. Okay. So we got one CHNO, right? So we have for this quantity, that quantity. Okay, let's go back again. So we see that carbon, you got what? We got 84.07 because it multiply. How many carbon you see in there? You got 7 times that. That's that number. So that's the hydrogen. You see 5 hydrogen, and each one is 1.01, something like that. You see 1.01. So we got 5 times that. So that's what's going on here. All right. So now you got 37.01% carbon, 2.22% hydrogen, 18.50 nitrogen, 42.26% oxygen. And these are all percentages. All right. This concept is very, very important. Once you have this, you might. So when you're in a lab, here's what happens. You're in a lab setting, supposing you're working for a company and somebody found something and we don't know what it is, but we did what we call classification test first. And then we found out we had carbon there, we have hydrogen there, we have nitrogen there, we have oxygen. Now we want to know how much to quantify. So these are the steps that the chemists will go through in a lab setting. And once you have this in percentages, then you put this together to find the formula for what that stuff is. It's a lot of work. All right. So you got to be familiar with that. All right. Now, so we talk about empirical formula, very, very important. What I was just telling you. So we find the empirical formula for certain material, and then from there we can find a molecular formula. For empirical first, that's the simplest of the whole number. We talked about whole number yesterday. They are part of the real number component. They start from 0. So we hear whole number, your reflection should be okay. I know what they are, they start from 0. They can't be negative. They got to always be positive. On the number line from 0 going up. So the empirical formula of a compound is the simplest whole number ratio. Ratio comparing two things, A to B, B to A. All right. Of ions, IONS, we get ion when the electron leave the valence shell or come into the valence shell. That's how ions are made. So when these time when the minute you sound them, right away your brain should start telling you, oh, okay, something leaving the valence shell, something coming in to resemble the column 18. That's what we're talking about. This is how, making that connection,
Question for the empirical formula.
Huh?
I have a question. So I see that it says like carbon 6, hydrogen 6, and then it goes into the empirical formula and it just shows CH. But then the one below it, it's basically divided by 2 instead of a whole number. I'm just trying to understand exactly.
Yeah, we're coming to a number. Let me finish this.
Yeah, of course.
So the ions, meaning what? Something coming into the valence shell, something leaving the valence shell in the formula unit. So atoms of each element in a molecule. So we have a molecular formula of benzene is C6H6. That's a formula for the molecule. Okay? But the empirical formula of benzene is CH. All right, so that CH is multiplied by 6. So the empirical formula is as simple as the empirical formula tells you what kind of atoms or element you have. Now going back to this here, all right, we can find an empirical formula from here, from this thing here. This is how you find an empirical formula. After you do all this work here, you find an element that are present, you can find an empirical formula. So we see that the empirical formula for benzene, what is it? What a carbon? Carbon is 12, right? And hydrogen is what? Is 1 in this case. All right. So you got this right here. And so this, if you multiply this by 6, you have this. Here you got a molecular formula of octane, which is this, C8H8 here. The empirical formula for this is what? C4H9. All right, so that means you multiply this empirical formula by 2, you get a molecular formula. All right, you multiply this empirical formula of benzene. When you do this here, find the percentages, divide each one by, we're coming to that later on. So this is how the empirical formula is made. But what they're saying, if you divide this number into that, you get that. All right. So we can calculate the empirical formula of a compound from its composition data. So now this is what we're going to do. Thank you. You better understand this. For instance, we can determine the mole ratio of each element. All right. From the mass to determine the empirical formula of radium oxide. See the question mark meaning the subscript, we don't know the subscript. So after we find the empirical formula, then the empirical formula will allow us to know what the subscript really are. So here's an example. Let's follow this one for understanding. So you got 1.640 gram sample of radium metal. Okay, somebody came in and came to your lab and said we got 1.64 gram sample of was heated to produce this. Okay, it went up from 1.640, it went up to 1.755 because of the oxygen that is combined with this metal. So therefore the weight went up. So then you have, remember when Mendeleev was putting the elements on the periodic table, he reacted them with oxygen. So, and the reaction of those metal in the same class, the reaction was the same for those metal. This is how you put the same thing we're talking about here. What is the empirical formula? So here's what happened. So you got 1.640 gram of Ra, and you got 1.755. So you subtract the 1.640 from the total, which is with a combination of the oxygen. Now you got 0.115 gram of oxygen. But this is all in gram now. All right, let's watch this now carefully. I'll come back and explain to you. All right, so the molar mass of radium, we go to the periodic table, okay? You go to the periodic table, you see it there. That's why the periodic table is very, very important, okay? And it's 226, all right? It's 226.03 gram per mole. And the molar mass for oxygen is 16.00 gram per mole. You find those. So you start with a 1.640 of the Ra, using the molar mass factor, that gives you the number of moles. All right, give it number more Ra. Then we go after the oxygen, we got 0.115 after the subtraction, we got 0.115 grams of oxygen. Using the molar mass, we got 0.00717 moles of oxygen. So everything is in mole now.
When you say that you subtract to get the basically the second formula to solve for oxygen, what are you subtracting from exactly again?
Okay, going back here. You had this metal Ra, right? You got Ra, and you heat it up, you heat it Ra up, and you weigh it first. It weigh 1.640 grams. You see that?
Yes.
Then you reacted this with oxygen, and the weight went up 1.755. You see that now? So if you want, we want to know how much oxygen we're talking about here. In order for you to know how much oxygen, we have to subtract the original number from the total.
Okay.
You got that now?
Yes.
And when we do so, we got 0.115 gram of oxygen.
Okay.
You see that now? So that's in grams. So we're gonna find more, number of moles for that. So we're gonna find the mole of each. So what is the mole of Ra when you have 1.640 grams of Ra? Go through the process here. The molar mass times that give you this number of moles of Ra.
Right.
Oh, the oxygen we use, go ahead.
No, nothing. Continue. Sorry.
The 0.115 gram of oxygen, find out how many moles is that? It's 0.007. So take a look at those two numbers. Which one do you think is bigger?
Oxygen.
719.
719 is bigger? You sure?
That's the mole, isn't it? Like the
Yeah, but just compare the two numbers. Tell me which one is larger.
Okay, then the radium one.
Exactly. 0.00726 is bigger than 0.00719.
Okay.
So you take this small number, divide by itself. You take this small number, divide the number by 0.00719, and then also divide this number, the large number by the small number. Divide the number by 0.00719. All right? So when you do that, you get something like this. But the subscript must be whole number. So we're going to round this off. So now you get RAO. You see that now? The RAO is your empirical formula. You see how we get an empirical formula? You must find the grams and then change the gram into mole and then find the smallest number and divide throughout. If you have 4, 5, 7 things, you divide by the smallest number. All right? So this is the empirical formula. Any question on that?
Yes. So the RAO with no subscripts, then is it be
There's one, but we don't have to write it there.
okay? Okay.
Okay. If you don't see anything there, you know it's 1. Okay. So we can also use percent composition data to calculate empirical formulas. All right. So let's assume that you have a 100 grams of sample. Acetylene is 92.2% carbon and 7.83% hydrogen. What is the empirical formula? Okay. Just like, let's go back to here, we could find the empirical formula here. All right. So let's see this now. That's how they find the empirical formula. Okay, so now we have percentages. All right. So what is the empirical formula? So if we assume that 100 grams of sample, so you change the percent quickly to grams. The percent, just remove the percent sign and stick gram there. You change the percent sign to gram. Everybody see that? We'll get it little by little. So instead of 92.2%, now we got 92.2 grams. Everywhere you see percent, put in grams. Instead of this 7.83%, we put in 7.83 grams. So now when you're in grams, what is your next move? Anybody? Can somebody tell me what's the next move from gram? Where do you go? When you're in grams, where do you go? Do you remember the trampoline? Where do you go? Nobody remember? You go to mole. See, that mole. You start thinking about going to mole because you're going to do empirical formula. So you got 92.2, 7.83 grams. All right. So that's what you got. Now, here's what happened. We're going to find out how many moles of carbon out of 92.2 grams. The molar mass for carbon is 1 mole of carbon is 12.01 grams. So we got 7.68 mole carbon. How many moles of hydrogen? 7.83 gram hydrogen. 1 mole is 1.01 gram and 7.75 moles of hydrogen. Tell me which number is a smaller number.
Hydrogen.
Hydrogen is smaller?
Carbon.
Carbon, yes, 7.68. So we divide 7.68 by 7.68. Then we divide 7.75 by 7.68.
Okay, so when you have the 12.01 grams of carbon and the 1.01 grams of hydrogen, those numbers, are they on the periodic table or?
Yeah, they're on the periodic table. Yeah. Uh-huh.
Okay, perfect. Thank
All
you.
right. So now, when we divide, we come out with what? 1.001. So we're going to round this off. So what is the empirical formula? CH. The simplest formula, CH. Just like we have for benzene, that we just saw that CH. Okay. So now, so the question was, what is the empirical formula? We have that. The empirical formula for acetylene is CH. It is also for benzene. So many things can have the same empirical formula, but the molecular formula makes a difference. The molecular formula would decide what you're dealing with. But so many things can have the same empirical formula. So this represents the ratio of C to H atoms on acetylene. So the actual molecular formula is some multiple of the empirical formula. So we say N, some multiple. So CH, the quantity of CH multiplied by N. This area is very important. When a chemist is in a laboratory setting and trying to figure out what something is, this is what they do. This is what they do. To tell you exactly what. So if we are told that acetylene has a molar mass, now, if you are given the molar mass to be 26 grams per mole, we're going to find out where N is from that. So how do you find N? We go to the empirical formula. so therefore we know that we got carbon is what? Is 12, hydrogen is 1. So the molar mass for the empirical formula is 13. We're going to divide the empirical formula by the molar mass of the substance. All right. So therefore, since the empirical formula is 13, then we're going to divide this into 26. So NH2. So NH2. Now we can go back here and multiply CH by N. So the molecular formula for acetylene is C2 and H2. Ever see that? It's fascinating, isn't it? So now you can tell your supervisor, say, oh, that was acetylene. Then maybe the guy on MSNBC or ABC would say, oh, some guy found so. And that was acetylene, but he didn't do the work. He's a chemist. They don't even call his name. So therefore, this is how that's the process. Ever see this process? It's a very unique process. Any question on this?
Yes. Can you explain again how you got the 26 and 13?
Okay. The 26 gram per mole is given to you. That's given to you. Okay. From the fact that you have carbon is what? 12, so 12 times 2. Hydrogen is 2 times 1, right? Well, what is 12 times 2? 24, right?
Yeah.
24 plus 2 is 26. That comes from the periodic table, when you do all that, right?
Okay.
But the empirical formula is something you did for calculation. So you got to also find the molar mass for the empirical formula. Carbon is 12, hydrogen is 1, so it's 13. You see that?
Yeah. Well, would those numbers be given to you in a problem, or you would have to figure them out?
Like the 13?
Yeah.
Yes, that's something that you find after you find these elements. Then go to the periodic table and see what is the weight for whatever you found.
Okay. Yeah. For carbon and hydrogen, it equals 13 if you add their masses.
Exactly. Yeah.
Okay.
You see it now?
Yeah.
They divide that into the molar mass of the compound. That will give you N. Then you go back and multiply that N by the empirical formula in order to get the molecular formula. You see that now? The formula of the molecule. Is that clear?
Where does the other 2 come from?
What 2?
When you doing CH in parentheses and then an N.
Is it where the 2 come from?
Yeah, the other 2.
No, 13 divided by 26.
Because hydrogen is 1, right?
Hydrogen is 1.
And then carbon
is 12.
Is 12.
So that's 13. You see that?
Okay. I got you.
So you divided 13 to 26, and then N is equal to 2.
So N is always equal to 2? That's just a given?
No, based on this particular information we have, N is not always equal to 2, depending on what you have, what you're dividing.
So if you were to have different
yeah, N will be different. Yeah.
Okay.
Okay, for
it's because you said 12 times 2.
Say that again.
You said 12. You said 12 times 2, which gives you 24.
24, and
then you said plus it, and then add on 2.
Right.
That's why I got confused that.
The 2 hydrogen, which is 26, make it 26. You see it now?
Nah.
Well, look at you guys. C2H2. Each hydrogen is 1. So two carbon give you 24. The 2 hydrogen give you 2. That's 26.
Oh, so fill in the numbers to add up the.
Yeah, the molar mass. You still don't get it?
Yeah.
You got it now?
Yeah.
Okay, good. That's good. All right. So that's how you do the empirical formula. And that's that would be a test. I think I got it there. In 1911, Rutherford estimated the value of Avogadro's number to be this. Using alpha particles from, we talk about, alpha particle using the thing for that we talk about, the most recent measurement. So all of this, I just telling you how they got that number, okay? All right, so let's see. The Avogadro number is this number now. Remember that number, 6.02 times 10 to the 23rd. It's just like 12 things equal to a dozen. Remember that? And there's one more of any substance. One more of any substance weigh this much. Like 12 things of any, 12 of anything. It becomes a dozen. The molar mass of a substance is the sum of the atomic masses of each element in the formula. STP, when you hear STP, the temperature is 0 degrees and the atmosphere is 1 and the volume is 22.4. All right. Now, we can convert between the number of particles. And most of the substances use Avogadro's number. That's the number right there. We can convert between masses of substances, and most of the substance using the molar mass. We can convert between the volume of a gas at STP and most of the gas using molar volume STP. All right. So this is a percent composition, empirical formula, molecular formula. All right. So any question before we go to the next review? Go review the other stuff.
Professor?
Yeah?
Are you gonna do anything for attendance today, or it's not?
It's okay.
Don't worry about it. Okay.
Yeah.
Thank you.
Okay, so any questions so far before I go to the next? Go review. Somebody had a question from tip 7, for chapter 7, chemical reactions. Before I go there, any question over here? Is it clear so far? Anybody? Okay, if you can, if you don't have any question, I'll go to the next tip. And so I hope you have your question ready for chapter 7. I'm going there now. And so tell me where you want me to go.
I was just confused on the.
You confused on what?
Like on the first step, when you cross over the elements, I get confused on how do you know the ions.
Okay. Tell me what part of that?
Like I get confused how because I know some of them are set, how do you find certain ions? Is there a specific chart that you find it on, or
Oh, ion, IONS? Oh,
yeah, like if it's a positive or negative charge?
yeah, okay. Let's go back to the periodic table, okay?
Okay.
So in column 1, how many electrons in the valence shell in column 1?
1.
1. What does it take for any element to be stable? How many electrons must be in the valence shell for stability to be achieved?
Well, to balance out, and if it only has 1, then needs 1, correct?
How many electrons must be in the last energy level, which is the valence shell?
8.
8, yeah. Octet, okay? The octet rule, all right? But what happened is if you got 1, how many you need to achieve that goal?
7?
You need 7. It costs a lot of energy to go and gather 7. To gather 7, so therefore, what do you do? To achieve the goal of noble gas configuration, what do you do? What must you do to achieve that goal? Let's start with sodium. Sodium has 11 electrons, right? Do you have your periodic table beside you there, everybody? She has a question, maybe her question could be your question. So sodium gave away that 1 electron. And now it has 10. It has neon configuration. So because it has a neon configuration, it is not neutral anymore. It's an ion. Sodium ion. You hear it now? Ion because it lost 1 electron. And what is the charge? +1 because it gave away 1 electron. So everybody in that family in column 1 are doing the same thing. They all got 1 plus, 1 plus, 1 plus.
Mm-hmm.
Then we'll move over to column 2. Column 2, meaning they have 2 electrons in the last energy level.
Mm-hmm.
All right, column 2. You got it now?
Yes.
How many electrons do they need to reach the octet?
6.
6. But that's too much energy to go and collect 6. So what's the best thing to do?
Give away.
Give away what? How many?
2.
Give away the 2. So when you give away 2, your ion is what? 2 plus. You see that now? 2 plus. So everybody in column 2 are doing the same thing. Okay, let's jump over the transition matter because then we can't predict what it will do. Let's go over to column 13.
Okay.
Go over to column 13. Column 13 meaning what? How many electrons they have in the last energy level?
3.
3. How many more they need to reach the octet?
5.
Octet meaning 8. 5. It costs a lot of energy to go collect 5. So what must we do?
Give away 3.
Give away 3. So therefore, when you give away, it's positive.
Mhm.
All right? Those people that do give away, they are positive people, like your parents. They give you all the time when you were growing up. They give you everything. Because they are very positive people. The parents are very positive people. They give constantly give you. You're taking, right? All right. So therefore, the giveaway. So now, every time you give away, go and look at column 18. See how many more electrons left. after you give away and compare to see who got what you got left in column 18. And that is the configuration you're going to have. So if column 13 give away 3, say for instance, you have alumina, right? Alumina give away that 3. All right.
Mhm.
So you got, so how many left?
5.
10.
10. So which element on column 18 that got 10?
Neon.
Neon.
Yeah, so you got neon configuration. Look at sodium. Sodium got 11. Sodium give away 1. How many left?
10.
Sodium still got what? Neon configuration.
Mhm.
Take a look at magnesium. Magnesium has 12. Give away that 2. How many left?
10.
It
10.
still got neon configuration. You see that now?
Yes.
So they become iron. When they're iron, they got the noble gas configuration. So when they come together, now all chemical activities take place from the valence shell. So now we move forward. When we get to carbon, it's in the middle there, right? It got 14. You can either give away 4 or take, we'll get 4, right? So let's go past that. Let's go to 15, column 15. All right. So if you're in column 15, what is how many electrons in the last energy level?
5.
Valence shell. 5. So which is easier, to get 3 or to give away 5?
To get 3.
To get 3.
To get 3. So to get meaning negative. Just like kids. When we were growing up, we were the negative people. We always took for our parents. So now, if you get 3 to reach the octet, all right, so therefore, you will have what? What is the charge? -3 on you. You see that now? So your iron is -3. Then we'll move on to 16. If you're in column 16, how many electrons in the last energy level?
6.
So is it easier to go with 6 or to do what?
To get 2.
To
Go
get
get 2. To get 2. So when you get 2, what is that ion? Ion is what? It's
Yeah.
negative, right? Negative
Mhm.
ion. So do you understand the ion concept? Everything is happening in the valence shell. Valence shell. Did that help a little?
Yeah, I got that.
So when they come together to combine, they crisscross, okay? They gotta, we need a neutral compound. It gotta be neutral. So all the negative charge must equal to the positive charge so they can neutralize. That's the idea, okay? But if for instance, if you have lithium in column 1 going to column 17, you don't have, they 1, right? Column 17, what are they doing? How many electrons in the valence shell for column 17?
7.
7, so therefore they need what?
1.
They just need 1, so -1. So in column 17, somebody from column 17 is combined with somebody in column 1. It's just one positive, 1 negative. That's it. It's cancer. And you have a neutral system there. You see that there? You don't have to show any crisscross in there. But here where you show crisscross, that the guy from column 13 and guy from column 16, for instance, right? Column 13, what's happening? They're giving away 3, right?
Mhm.
Yeah.
So the charge is +3, right?
Right.
And the guy in column 16 is taking on what? 2
Yeah,
Oh,
minus
2.
2.
minus 2. So therefore, you got 13 plus 3 and minus 2. So they crisscross. The 2 go toward it. The one with the plus 3 and the plus 3 go toward the one with negative. So when you multiply the 3 by the 2, you get 6. Multiply the 2 by the 3, you get 6. Positive and negative, it can't neutralize it. That's why you do the crisscrossing. You see it now? Is that clear so far?
Sort of.
Oh, no, I'm not happy with this sort of. I'm not happy at all. So let's go back. What is it you don't understand? I want you to get it before I leave you. Tell me what you still don't get. What is it that you still don't understand? You do understand the Bohr model, right?
Yeah, I got a little confused with the crisscross part that you were talking about.
Okay, the crisscross. Okay, we want the charges to be equal and opposite, right?
Yes.
So if I got +3 over here
Sorry, Professor. You're cutting off.
and got -2 over here, what must I multiply by +3? What must I multiply by +3 to get +6?
Hello? You.
Can you hear me now? Can you hear me?
Yes, we can hear you.
Okay. So do you understand the crisscrossing now?
Yeah, I understand.
That's
They-
good.
confused, but I went back in my notes and I get it.
You got it now? Very good. Yeah, yeah. Well, let's go there. Let's go there. Okay, now we should look at the Nanahani equation. Which type of reaction we want to take a look at? You know, we got combination, decomposition, single replacement, double replacement, neutralization. Okay, let's go there. Let's go double replacement. Let's go double replacement.
Hello?
Hello.
Hello? Hello?
Single replacement. This is double replacement right here. This is a general one, okay? Okay, here's one right here. Double replacement. You see it? Okay, look at the reactants. Can you identify the reactants? You see them there? They're on the left-hand side. And the product is on the right-hand side. See that now? You see the BA in the reaction? The BA is taking the place of the potassium. You see it now? Now the potassium is K2 in the reaction, right? Because the chromate ion is -2. So you crisscross, you know, you see that now? So that 2 goes to the potassium to balance the chromium, okay? But when the barium takes the place of potassium, barium don't have to be Ba2 because barium has a positive 2 charge. So it will automatically balance the chromate, which is -2. You see it now? Okay. Okay. Yeah. Okay. This is a non-ionic equation you're looking at right here, right? What you're looking at now is a non-ionic equation. We're coming, yeah, to change the ionic equation, the next level, you would say Ba2 plus, Cl minus, right? Plus K2, K plus CrO minus 2, right? Then you leave the BaCrO4 is potassium, K plus and Cl minus, right? That is the ionic equation. So now, what's going to cancel? Barium, and chromate. So you have Ba plus 2 and CrO4 minus 2. This is a net ionic equation now. The third one will be Ba plus 2 plus CrO4 minus 2 equal to BaCrO4. That's the net ionic equation. The other ones are still in solution. So you don't have to be bothered with them in the third, in the net ion equation. You see it now? Okay. Now, tell me what I just told you. Explain to me. Say I come to you now for help. Mm-hmm. Huh? Yeah. Okay. So you got it? Or let's go over again. The first equation, BaCl2 aqueous plus K2RO4 aqueous, go to BaCrO4 solid plus 2 KCl aqueous. That is a non-ionic equation because we're not showing any ions. That's what non-ionic equations stand for. We are not showing any ions, okay? So the next equation, we're going to show the ion now by putting the pluses and minuses, negative and positive charges in the second equation. But we will not put it in barium chromate solid. It will be neutral there, right? Now the third one was show the barium plus 2, chromate minus 2, it goes to BaCrO4 solid. That's a net ion equation. You see it now? So from the solubility rules, see that table 7.2, I told you to have that table with you. That table is a guiding table in this process. But you must also balance the equation. First, balance it not ionic equation first. You see, is it balanced? Tell me if it's balanced. The non-ionic equation, is it balanced? How do you know it's balanced? What do you check for? Mm-hmm. And barium chromate. The chromate 4 is a polyatomic ion. Chromate is a polyatomic ion, yeah. Okay, you see that now? Okay, now look at the next one. Look down below. Do you see sodium chloride? See, look at the non-ionic equation. Sodium chloride aqueous, LiNO. That's a non-ionic equation. How do you write it, the ionic equation? No, sodium, watch it now, sodium. Sodium is what? No, sodium itself. What is the charge on sodium? Oh,
Positive one?
what? It's in column 1. Everything in column 1 we told you that they're all positive because they got one electron in the valence shell. They give it away that one electron. When you give it away, it's positive. Chlorine is accepting because it's column 17. So the sodium give that one electron away to chlorine. That make chlorine -1, and sodium become +1. And the lithium is also in that same column that sodium is in, so it's also +1. That the polyatomic ion NO3 is a -1. You see it? You go on the right hand side, sodium is still +1. Polyatomic ion NO3, so they are all, everything is in solution in the ionic equation. So there you don't have any net, there's no third solution, there's no third equation, because everything is out there in solution. There's no precipitate in that second reaction. You see that now? So therefore, you just write, once you write it, the non-ionic equation, the ionic equation, then you stop, because the ionic equation will let you know that you can't go any further because everything is solution. You see it now? All right. But the first one, we can see that there will be a net ionic equation. The barium one, you see that? That one had a VaCO4 is insoluble. Yeah, it's insoluble. Yeah, you got it now? Very good. And any other person who don't understand? Anybody? Any other question for chapter 7?
Well, for me, Professor, the
Yeah.
part that confuses me is because it's the lab that I was having trouble with.
Yeah.
So I know, for example,
What lab you in?
Dr. Ible.
Okay. Okay.
And I know that to get the products, you have to cross the products to get the reactants, correct?
The reactant must react to get product.
Right. So
And,
for me,
if it's a double replacement, it's just switching places in a product. In a product, they are switching places in the product. Where barium used to be, potassium is there now. What potassium used to be, barium is there in the product. Do you see that? That's double replacement.
so you just replace barium with potassium.
They just swap places, change places. But when they do that, the charges will also affect them. You gotta keep track of the charges as you do that. The charges are not changing, but now you gotta do double something or triple something. So in this case, in the product, the subscript for the replacement in the product is just subscript 1,1 because barium is +2, chromium is -2, and potassium is +1, and chlorine is -1. So the subscript is understood to be 1. But when potassium was with chromate had -2, so chromate needed another potassium to balance chromate. But once you left chromate, you don't need another potassium to balance the chloride. You got they're opposite and equal in terms of the charges. So this is all happening in a valence shell. You see that now?
Think so.
No, I don't think so. I want you to understand it. What is it you don't get it yet? Let's stay on it until you get it. We got time.
Well, it's just that I'm a visual learner, so I'm trying to like see it happening, but it's just hard.
Okay. But tell me the unperiodic table. Do you understand that part? What they give away, what they accept. They give it away.
I understand that when you give away, it's positive.
It's all happening in the last energy level. And taking on is negative. You understand that part? You don't understand it. And based on how many electrons in the valence shell, that's how you're gonna give away, that's how you're gonna accept. Okay.
Yeah.
Okay. Any other question? Anybody? Any area in chapter 7 that you want me to go to so we can talk? What about chapter 8? You have any question there? I can go back to 8 if you understand this. You have any question in 8? Because the exam is just around the corner.
Could you go over the empirical formula again?
Empirical, oh, very good. Okay, let me go back to 8. All right. Chapter 8. Okay. Empirical formula. Do you understand the definition there?
Yeah, I do. I just like
Let's start with the definition.
Hmm?
Do you understand the definition?
Yes, I just wanted to go over the bullet, the second and third bullet point.
Okay.
Are they like, do you use the greatest common factor to like make sure
Right here?
that the no.
Which one?
The slide before?
The slide before?
Mm-hmm.
That one? This one?
No, the one with the definition on it.
This one?
Yeah, this one.
The one with the definition.
Mm-hmm.
Okay, this one, right?
Yeah. I just don't really understand like how it goes from like C6H6 to CH and the other one CH18 to C4H9. Like, could you explain it again?
Okay. Okay. So this is they give you the molecular formula. Let's find a molecular. Okay, find a molecular formula for this. All right. How many carbon here?
6.
Okay. So 6 times 12 is what? Let's spend some time on this one. See you get it. What's 6 times 12?
72.
72. All right. How many hydrogen you have there?
6.
So 6 times 1 is what?
6.
So what is it? What is the molecular formula for benzene?
Could you repeat that
If you
again?
add 6 plus the 72,
Mm-hmm.
what do you get?
Uh, 68 or 78?
78. Let's find the molecular formula for the empirical formula, which is CH. What is it? What is it? Carbon is 12, hydrogen is 1. So what do you get?
When you multiply them together?
No, you add them. 12 plus 1.
13.
Okay. So now you got 78. Divide 78 by 13. What do you get?
6.
6. That's what's happening. See it now? But they didn't show it here. I'm glad you asked the question. They just gave it. So now, if you take that 6 and multiply by CH, you get C6, H6. That's what you see it now?
Oh, okay. Yeah, I see it.
You see it now, right?
Mm-hmm.
This slide didn't do that. I'm glad you came back to it.
Okay.
But this is what's happening. That's what happened in this slide. All right. Let's see. Okay, you see it right here?
Mm-hmm.
They give you the molar mass, and let's see. Okay, so that's, let me see where they did it. Okay, you see it right here? In this one, they give you the molar mass. You just found the molar mass. You see that?
Right.
The empirical formula is also CH, right?
Right.
By acetylene. So many things can have the same empirical formula, but a molecular formula will make the difference.
Okay.
Benzene is CH, acetylene also CH, but it told you that the molar mass for acetylene is 26, right?
Right.
Well, you have to figure out the molar mass for the benzene. You got to give it a molecular formula. You got a molar mass for the molecular formula to be 78, right?
Right.
But the CH is always going to be 13, right? So you divide the CH, the width of the CH into whatever formula, molar mass you got to make the difference. You see, because this guy, molar mass is 26. So his formula is C2H2. Whereas benzene is what? 78, right?
Right.
So therefore it's C6H6. You see the difference now?
Yeah, I see it.
It's making sense now.
Mm-hmm.
But I'm glad. I'm so glad when it makes sense. So that's so you can have so many CH everywhere or so many compounds, but the molar mass will be different. You see that now?
Yes, I do. Thank you so much.
Okay. Any other question, anybody? Everybody doing okay? No question? So did you all got your study notes, topics to take a look at? Spend some time on for the test. You got that? Okay, let me see if I can go to it. Yeah. Yeah. Uh, what you say you saw the midterm? Oh, the notes. Oh, yeah. Uh-huh. Yeah. Oh, no. Just A, B, C. You do the calculation. If it's A, you just, do the A. Yeah. Uh-huh. So that's just A, B, C. That. If you are in a regular setting where you're using Blue Book to do your exam, then I'll be looking for your work. But I mean, where you need to practice so you be study to make it easier to find those correct answers. Okay? All right. All right. So any other question? If not, you're free to go. All right. So for those of you that are in my lab, I'll see you this afternoon.
Professor,
Uh-huh.
how many questions are we going to be having for the midterm again?
I think between 10 and 20, something like that.